Alright, hello and welcome to the last week of classes. We're just going to review for the final and take as long as we need to take for that. Do come to office hours if you have any questions about anything. Obviously, I can't give you everything in lectures, and also I don't know what's confusing to you specifically, so please come to office hours if you'd like to, if you think it would help. One thing that I have made for you, as usual, is a fancy cheat sheet for the final. I worked very hard on it, as I do. So information about recursion, exceptions, bitwise operations, and makefiles. So we'll talk about those later. But let's jump right on into it with talking about older things that did appear on midterm 2 and before midterm 2. You're just not allowed to forget these things, so we're going to review them, okay? You'll definitely need them for CSCI 41 if you need to take that. Okay, so the first topic that I want to talk about is references. So let's just go from scratch. What is a reference? It's just an alias for another variable. It's like a secret agent, and it has its own special name. So if I have like an int x sitting around, and then I go and I say int reference, the ampersand means reference. You attach it to the type, and now you read it backwards. It's like, oh, this is a reference to an int. Maybe we'll call it r. And then you say it equals x. But this r is not a separate variable. In memory, if I get fancy with my colors, r is green. In memory, maybe x looks like this. It's its own little box. It's an int. It's 32 bits long. And it holds 42. But this line here makes r a reference to x, and therefore it has the x and r are aliases for one another. Okay, so r is just another way of talking about this box. Okay, it's the same box. If you say r++, it's the equivalent to having done x++. Okay, that's very important. Things like that. Those are equivalent, and many other things can be equivalent. So a reference, it's just an alias for another variable, and we like to use references across function calls for one of two reasons. We like to use reference parameters because, reason one, we want to touch the memory that was living in some other function. And references allow us to do that. Also, and this is going to be very important if you take CSCI 41, it also allows you, if you use a reference parameter, parameter of a reference type, it allows you to not have to copy anything because you're using the original value still. So we also like to use const references. Okay, so just to show you some examples of those, let's do our swapping ints example. So like we got x, we got y. We want to swap them. We want to make a function that works like this. We say, well, x is 42, y is 43. In main, perhaps, maybe I should make this much smaller if I'm going to draw the stack. Down here in main, maybe that's where x and y live. But we want to call swap. Swap ints or something, who knows, on x and y, and we'd like to, like this to do its thing, like it's got a magical cloud of whatever, and once it finishes, x is now 43, y is now 42. That's what we want to happen. Okay? So call by value and call by reference are the two ways that you might think to do this, but call by reference is the only one that has the correct answer. So call by value copies things, doesn't touch original memory, and call by reference uses the same, uses a different name for the same place in memory. All right, so let me just show you that quintessential example of references, and we'll go from there. All right, so we'll say references.cpp, and here's an x equals 42, y equals 43, and we want to do something like swap ints, because there's a swap function in the C++ standard library that I don't want to accidentally use. So we'll make that function, then we'll see out x and y. Okay, so we got to make this, and the wrong way is call by value. Just copy stuff. So remember this, int swap ints bad. Let's say int a, int b. It's like, oh yes, I'm going to swap a and b because those are x and y, but it's not going to work because they're copied. So a holds a copy of x, b holds a copy of y. It just won't work. Even though you can go through the motions and be like int temp equals a equals b equals temp. Oh, and this should be void. But lo and behold, nothing changed. Oops, and I forgot the y. X is still 42, y is still 43, because this swap int's bad is called by value. So x is, a is set to this x, but it's just a copy. It's as if, like right before this got called, it's setting up the member variable, or it's setting up the parameters. It's like, okay, int a equals mains x. That's essentially what it's doing. Int b equals mains y. And these are new places in memory. That's no fun. But we can make this work by adding references. This is the right way. Call by reference. So the way that these get called now, the way that this function gets called is, if I actually go and call it, there we go. The way this works is it's setting up its parameters. It's like, oh yes, I need to instantiate my parameter int reference a. Oh, that's equal to mains x. And now you can see why this a is going to actually be the same memory. No pun intended. Okay? Because the references, it's setting up these parameters in this way. You can think that this is what happens when you call this function. It's like, okay, I need to instantiate a to, oh yes, to the x. Cool, now it's a reference. Touching a touches x. Okay? Bam, it actually did the thing. Life is beautiful. Okay, so that's references. And the other nice way to use references is to make it so that you don't copy values across function calls. So like, if I make a gigantic vector, let me do that. A huge vector, I'm going to have to include vector, of course. If I make a giant vector, vector int v, I don't know, let's have it hold, I don't know, 10,000 of the, I don't know, 42, like 10,000 42s, okay? So, just to prove to you, v is huge, and v holds 42 at every index. Let's do that. It's giant, and every index holds 42. That's one of the vector constructors that let you do that. And then we can like be like, oh, I want to do, I don't know, the sum of all the things in the vector. So see out sum of again, I think there's probably a standard library function called sum, so we're just going to make our own called sum vector. And what you don't want to do, bad, is take the vector by value. It's like, oh, yes, I'm going to copy the giant vector. We don't want to do that. And maybe you don't have enough memory to even do this. So that's no fun. Don't do that. Do this instead. Take the vector by reference. Now it's not getting copied. And even better, make it const. Because this function's not supposed to change its values. It shouldn't if it's implemented correctly. Okay, so make it a const reference as well. And then you can be like, all right, int sum equals 0 for int v x in v, sum plus equals x, return sum. All right, and then it'll just work. It might actually overflow the ints. Oh no, it works. Cool. Yeah, 420,000. Makes sense to me. Okay. References. Now you're experts. Classes now. So I just want to give examples of classes. You know what they are. By now you've used them enough. They're just, well, you know about structs. They're just a data value. Well, let me try to explain it in words. Classes are structs with associated member functions. I don't know. Classes have member variables and member functions. Okay, you instantiate a class by making objects of that class. And you can kind of talk to those objects by sending them, we call them messages. Like, hey, what's your field's name? What's your field's value? Please respond to this method call, things like that. So at a high level, that's what a class is, and you know about it very well now. You've even kind of implemented them yourself. So I won't waste your time too much. Let's just go into examples because I have some cool ones. So the first example is a stopwatch. So I want to be like, okay, stopwatch.start, and then it'll just start tallying up the time since a certain starting point. Okay, so it's going to like save the current time, and I need the ctime library, so let me go and open that for you. So here is the ctime library, and it has some nice functions. I think I've talked to you a little bit about clock once upon a time, but we'll use time this time, like as if you're seeding a random number generator to get the current time. And then we'll use diff time on what time gives back. So time gives us back a time t. It's just their struct type that holds like hours, minutes, and seconds or something. And diff time takes 2 time t's and end in a beginning, and it gives you back the number of seconds between those 2 times. And we can use that as a stopwatch. All right. So that's essentially what I want to do. I want to be like stopwatch.start. Okay, and that will call different methods inside of this stopwatch class as well. So let's do this. It's going to be exciting. So I'll make a new file called stopwatch, or maybe, yeah, stopwatch will work. So here's how I want to use it. I want to be like, all right, I want a stopwatch s, and I want to start it. Okay, so I'm going to call the start method on s. And that's essentially all I want to do. I'll have to like quit the program to actually stop the stopwatch, but that's okay. This will just like start the timer. Are you ready? So we need ctime. And here's how we can do it. Class stopwatch. It's going to have, well, it doesn't actually need a constructor, because that doesn't really initialize anything. We're going to wait to start the stopwatch until later. Maybe we can have the constructor start the stopwatch, but no, I think we don't need a constructor actually for this. Whee. So no need for a constructor. We'll set member variables in start. So there's going to be a start method, that's for sure. And that's going to have to keep track of some things, okay? So something we don't want anybody to see is the starting time. Because the stopwatch is going to start, and we're going to need to record that time so that we can display the time elapsed between the start time and the current time. Okay, so we're going to have a time t start time. Okay, and so start's going to set that. It's going to be like, all right, start time equals get the current time. And you say time null or time 0, time null pointer. That's how it works. And you know, let's be fancy. Let's be good programmers. Let's actually implement this outside in full. So void stopwatch ::, and then the rest. Start. And there we go. That's more like it. And then we'll have some actual private methods, in fact, because when the stopwatch starts, we want to start displaying the time as well. Okay, so save the start time, but also, yeah. And now, continuously, keep getting the current time and displaying the difference between the start time and the end time. Okay, so it's like while true, like forever, until the user kills this program with Control-C, keep getting that time. Like let's make a private method that's called, I don't know, output time elapsed, or output time since start. All right, so let's make a method that does that. We'll call ourselves. It'll be a private method so that the user can never use it. It's just for us, the implementers of the function. All right, so void output time since start. And we'll go and implement that now. And what we'll do is we'll get the current time. That's a time t. Current time equals time 0. That's just how you call the time function to give you back the time with a 0 or with null pointer. And then we'll get the difference between start and end, and that will be going back to the documentation, diff time, end, and then start. And that is current time is the ending time, and then the start time, which is our member variable, is the starting time. Okay, then we'll output it. We'll be like time elapsed, and then S. And let's compile and run this. Cool. It's kind of working, but that's not good enough. That granularity is too tiny for me. I'm not happy with that. So I think instead of using time, maybe we'll use clock instead, because this is just like not enough. Not enough granularity. So we can use clock and then clocks per second. Okay? So let's change all of this to do that. So instead of start time being a time t, let's make it be a clock t. If I can show you that. Clock returns clock t, doesn't take any parameters. Okay, so we're updating based on new information, like our user doesn't like having seconds without decimal places, so we need better granularity. So we're going to use clock instead of time. So start time is now clock with no parameters. Okay, you see how we're changing all this? We're refactoring our code. Clock, please. Clock t. And now, the number of seconds between start and end, it's, well, you just subtract. Current time minus start time divided by clocks per sec. But we first need to convert one of these to a double, otherwise it's going to do integer division. And that should make it a little bit better. Better granularity, at least. Look at that. Now it's counting up. It's counting up, and it's displaying the time elapsed. This is kind of ugly looking. It's like it's writing a million lines a second, just trying to display the time to us. Let me tell you a bit of a secret. Your book might have actually taught you this, but let me teach it in class for once. What you can do is, you know, \n. Okay, it has cousins though, and it goes back to the typewriter era. If you know what a typewriter looks like, it's got like a bunch of keys, and you got the paper up here, and you have the little thing that it's typing along, like, I don't know, it's a little cylinder that types along, and eventually, like the current place where it's typing, it gets over here, and it dings, right? Ding. And it's your job as the person who's writing this file on a typewriter to like move it back this way so it can start typing on this side of the page again. Okay, and that's what's called a carriage, or sorry, that's what's called a line feed, I think? No, sorry. It's called a carriage return. What we want to do in the age of typewriters is return the carriage to be back here, okay? And back in the day, there were terminals that you could connect to that didn't have screens, they just printed out to a page. And so there is a special character called \r that performs a carriage return, as if your terminal was a typewriter. So it'll just like go back to the beginning of the line and start typing again there. Okay? And so if we say \r before we print out anything, it'll just keep typing on the same line because it'll return back to the beginning. Okay? And we actually don't want to end the line ever. We just want to keep going back to the original, keep going back to the start of the line. And overwriting things. In a terminal, it overwrites. On paper, it would just keep on typing like over what it already had typed. But that's the magic of technology. So now it's typing on the same line. And this is much cooler looking, I think. You can still see like how it's like moving its cursor as it types. That's a little bit of a relic, and there's a way to turn the cursor off, but that is a bit too fancy right now to teach you. But this is a stopwatch, and it's all on one line, and it just keeps updating the line, so I can't really select it, which is fun to think about. But now it's just counting. You now have a stopwatch, and you implemented it in C++. How cool is that? And just Control-C to stop. Okay, that's a cool example of classes, number one. A cool example of classes, number two, is a calculator with buttons. But actually, before we get there, let's see. Is any of these... Technically, this one can be const. Before I forget, this one can be const because it's not changing anything. Start changes the start time member variable. This one doesn't touch any member variables, it just uses the start time. Okay, now I'm happy. Let's edit a file called calculator.cpp, and this is a bit of a fancy example. So we're going to implement a calculator with buttons. So it's going to be like calc.press 0, calc.press 1 before it, hopefully, and then be like calc.press enter. So one button at a time, we can build up a number. Okay? And so what I want to do is model this, and then we'd like, this is press the equals sign or something instead. you're going to press a single button at a time and build up numbers somehow, and then you'll press a command to, okay, get ready to type the second number to add, to subtract, to multiply, to divide. And then finally you can press equals to perform the computation. And so we can model this as a state machine, if you remember that. The start state is like, okay, we're ready to read the first number on the calculator, and the user can type all the numbers, and it'll just start remembering the current number that the user has typed. So each time it types a digit, we build up our first number more and more. Okay, there's a way to do that. And then the user is eventually going to type an operation. And then we know, okay, we have a first number, we have an operation, now we're just waiting for the second number, so let's read that with all the digits we might need. And then the user is going to type the equals sign, and we'll be ready to compute an answer, display it, and then go back to the starting state to do this all over again. Okay, so we just kind of, without any input at all, we just go back to the start state. And eventually you'll learn that the way you do that is with a character called epsilon that denotes the empty character, empty string. That's beside the point, though. This is the chain of command. We read the first number, as many digits as it takes, read an operation, read the second number in the same way, get an equals sign and compute the answer, display it, and now we're back to the start. Okay, so it's kind of a lot going on, and obviously I'm not going to test you on something this complicated, but it's a great example of classes, I think. So let's do it. So eventually I want to do this. Calculator, calc. And I want to, let's do, 42, times 57 or something. And so here's what we want to do. We want to say calc dot press 4. Calc dot press, press 2. Okay, then we press times. Then we press 5, because now we're typing the second number. Then we type 7. And then we press equals. Or enter, whatever we want to call it. And then it should display the result of 42 times 57, whatever that may be. Okay, so that's how I want to use my calculator. So it's got to save what state it's in so that it can actually calculate these things. Are you ready? So let's do our private member variables first. What do we need to know in order to make this work? We need to know what state we're in. So let's keep track of that with strings, just for fun. Current state. So I'll need strings for that. And then we're going to need to keep track of our first number, our operation, and our second number. You see that? That's the data we need. So int first number, second number, and then maybe for their operation it can be a char operation, or op. Let's just save it like that. So I think that's all the data that we need. And when we initially make a calc in the constructor, we should zero out everything, right? We should make sure that all this stuff is set to good enough random values, or zero out the things that need to be zeroed out. So let's do our constructor now. A calculator should start out, or we can do this outside again. It should start out, with zeros for the numbers or something, right? So let's do that. We can use the initializer list if we'd like. We can say, well, the current state needs to start out as waiting for the first number. Read the first number. Let's say that. That's our first initial state. Then the first num can be 0, and the second num can be 0, and we can leave the operation undefined because we're not really going to care at the moment, I don't think. So, are you ready? I think we're ready for some operations. In the interest of time, I'm only going to implement these press buttons that we actually use, so 2, 4, 5, and 7. So we're going to have a press 2 method, press 4 method, press 5 method, and a press 7 method. I encourage you to like make them all make every last one of them from 1 to 9, but my example only needs these, and I'm going to just leave it like that. So, knowing that our first number is a 0, we need to build up. We need to add 2 to the end of our number, for example, when this is pressed. So how do we do it? We want to go from, say we have the number currently, like we've built up 12, and the user types like let's say it's 15. And the user types a 2. We want to add a 2 to this number. How do we do it? How do we turn this 15 into 152? Well, if you think about it long enough, the answer is multiply by 10 to get 150, and then add 2. Then you have 152. You've added another digit at the end. Okay? That's how we do it. So press 2. Might as well do this while we're here. We need to add a 2 to our current digit. So we need to figure out which state we're in. First of all, if we're reading the first number, we need to add to the first number. If we're reading the second number, we need to add to the second number. You see that? So if current state equals read first number, well, then we need to add the 2 to the first number. Otherwise, else if current state equals to read second number, then we'll add it to the second number. Otherwise, the user did this in the wrong state. So we don't care anymore. Okay, so we'll add to the first number. We'll say first num equals first num times 10 plus a 2, because we just pressed the 2. Otherwise, we're doing this for the second num. Yeah. Cool. And then we're going to do the exact same stuff for the 4, the 5, and the 7. Whee! Every time they press the 4, we're going to add a 4 to our current digit, if it's the first number or the second number. Otherwise, we do the 5 or the 7. Okay, so instead of a 2, it's going to be a 4 here. 5 here. And then a 7 here. And a 7 there. So that should do it. So now we should be able to build up our numbers. That's quite nice. 2, 4, 5, and 7. And let's see, what else? Now we're going to need to have an operator function. So if the user presses times, we need to like save the fact that we're ready to calculate the times. Okay? So, are you ready for press times? Let's put it up in there. Okay, so press times. Remember what needs to happen. We need to, when the user presses the times button, we need to advance to the second number state and also save which operation. Okay, so if we can only do this if our current state is read first number. Otherwise, the user did something silly. If that's the case, we will set our operation to times, and then we'll set our current state to read second number. Okay, so now we're ready to read the second number when the user types or presses more digit keys. Okay? Isn't that quite nice? And so then we're ready to read the second number, and we've actually handled this because we implemented that case already for all the digits. And then finally, when the user, I encourage you to do like the plus, the minus, the divide as well. Now the user can press equals to display the answer. Okay. Void press equals, and what that'll do is it will compute the answer and then get us ready to do it all over again. Okay, so the user can only press equals. It only makes sense to press equals when we have two numbers. So we need to be currently in the read second number state. Okay? We technically don't even need to save the press equals state, or the compute answer state. So if current state equals to read second number, then we will compute the answer, display it, and go back to the start state. That's what I wanted to do. So, and answer equals first number, something, second number. Well, we're going to need some cases, aren't we? If operation is equal to times, all right, let's do plus and times, even though we don't have a plus. You should do them all, of course. Then the answer is first num plus second num. Else if operation is equal to times, then the answer is first num times second num. Then we display the answer, like the screen says, answer. Or you know what we can do? We can give back the answer. How about that? I like that better, because then we can test it. Go back to the start state and give back the answer. So let's return it. And then now we're going back to the start state as well. So we can read another number and do it all over again. Alright, so we're going to make this int, return int. We're going to make this int for return int, and then we're going to output the answer. Okay, let's see if it works. 42 times 57, well, what's that supposed to be? 2394. Oops, what have I done? 84. Oh, oops. Yeah, if the user did something silly and didn't press the button in the right state, let's just return 42. We should never get there. We should yell at the user. We should throw an exception, honestly. We'll get to exceptions later, though. Hey, it's 2394. Awesome. And so the very last thing that I want to do is make a test for this, so you remember all that. So if b cout passed, else is going to be failed. And then we'll have void test calculator. So remember how to make a test. You do what you wanted to do and compare it against the right answer. Get the result, get the correct answer that it should have been, and then you assert that they're the same. And then we now have a test for our calculator, and you should make many of them. Again, what have I done wrong? Line 93, no return statement. Ah, yes, excuse me. That should have been void. My bad. And we passed our test, which makes sense. Okay, so don't forget how to test things. That's all I got for you. You're going to be using classes for the rest of your life, so you gotta get those ingrained in your mind. And pointers are going to come up. Pointers and the heap are going to come up quite a bit in CSCI 41. So please pay attention if you have to take that. And obviously you'll probably see them on the final. So pointers. A pointer is a box in memory that holds the address of some other thing. It holds, let's just say it holds addresses. Okay? So the idea is that's very different from references, even though technically references are implemented using pointers under the hood beside the point. You can say, all right, int x equals 42, and now if you want to point to x, like here's x over here, if you want to point to x, you have to say int star p equals address of x, okay? So remember your star in the type, ampersand for address of, and then star in an expression to dereference. Okay, so now we have p pointing to x, so p holds whatever the address of x was. Maybe it was 100 or something. So now p's pointing to x just like that. So now star p, I don't know, plus plus, is equivalent to x plus plus. Okay, you gotta dereference the pointer to go to the place in memory that you want to change. All right, so let me just show you a bunch of examples with int pointers, and then we'll do a fancier one. Dun, dun, dun. Let's see here. So int, I don't know, int x equals 42, int star x, or int star p1 equals the address of x. So now p1 points to x, and maybe so does p2. And now maybe p3 points to p1. And if you want that, it has to be a different type. It's an int pointer because we're pointing to an int pointer. Weird, huh? P3 points to P1, who themselves point to X. Okay. Do I want to go any farther? Why not? Int star 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 P4 points to P3. To P3, who points to P1, who points to X. Cool, huh? So you can think about it as the number of stars that you need to get to the final int. So cout, I don't know. You can change X in all these different ways. X plus plus, P1, dereference it. I don't actually know if the P1 plus plus is going to work in the right place. Yeah, star P1 plus plus, star P2 plus plus, star star P3 plus plus, star 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 P4 plus plus. Oops. These will all increment X. So 43, 44, 45, 46, 47. We can output any of them because they're all X. Okay, I'll just output X. Why not? Hey, we got 47. Cool. Okay, so just to show you how this is working, it's got in code, we have, yes, we have all this. I think we called it P1. All right, so x was 42. P1 held the address of x, pointing to x. P2 also held the address of x, pointing to x, right? Yeah. P3 pointed to P1, so it held the address of P1, pointed to it. And then P4 held the address of P3, therefore pointing to P3. And so these are just numbers. I can make them up, or I can just say ampersand stuff just to make it easier in your mind. But these are numbers. If you try to print them out, they're going to be weird looking. They're just addresses of memory that are displayed in hexadecimal notation. So like, I don't know, P4 or P3, it looks like this, which is useless to you, but if you dereference it twice, you're going to get an int back. You know where x is based on this. Okay? So that's just a bunch of int pointers. And then don't forget how to do pointers to a class or to a struct. If you want an element of that thing, so if you have a pointer, if you have a vector int pointer, for example, then if you want the size of it, you have to say, if it's called, I don't know, VP for vector pointer, you can say vp.size, but you can't. This is the one you can't say. You have to say star vp to get the actual vector. Then you can say .size. Or alternatively, you can say vp arrow size. Okay, that's what I wanted to say about that, really. So here's my vector. If I want to go and do stuff like cout, there. If I want to pointer to this vector, first of all, vp equals the address of it. Needs to hold the address of v itself. And now if I want to do stuff, I got to say either star vp dot size, because I need to get the underlying vector somehow. vp.size makes no sense because it's a pointer, it's just a number. There's no dot on a number. Or I can say vp arrow size because everybody hated putting parentheses and dereferencing. So they built this into the language. Okay, so either way it works. I tend to use this for reasons, and this is just a very pedantic way of saying what you're trying to do. Alright, so that's pointers. A pointer is just it's a place in memory that holds an address. So it's a place in memory that has another place in memory. And remember how things are arranged in memory as well. It's just a big table. Addressable by bytes. And address 0 never exists. It's null pointer. You can never dereference anything that points to null. And if you want to store multi-byte things like ints are 4 bytes long, have a starting byte. And then they just take 3 bytes after that, or 4 bytes. So for example, if I have the integer in memory, like here's int x, if I really have int in memory, int x in memory, maybe like here's address, it starts at address 100, the number 42, it's going to span, like here's address 99, 101, 102, 103, 104. The integer itself is going to span these 4 bytes, okay? That's what an int is. It's 4 bytes long. And so somehow it knows, like it starts at address 100, maybe this is address 100, and this is all going to store 42. And you know actually how it's going to store 42. It's going to have a bunch of zeros and then the binary for 42. That's the idea. And the order in which it does it is weird. We don't have to get into that in this class. You'll see that in CSCI 45, that's for sure. Okay, so that's my rant about all that. And so now let's go to the heap, where you need to know about pointers anyway, so that's why I put that before. So the heap is a magical place. Dynamically allocated memory is what it stores. So on the fly, you can make something. You can make an int, and it lasts for as long as you want it to last. So new int, you make stuff on the heap with the new operator. And you can think of the operator new as returning, we just say that, returns a pointer to an int. A pointer to that new int you made on the heap. And if you want to get rid of it, you say delete. It takes a heap pointer and deletes it. Okay, so you can manually manage your memory like this. You can say new and delete, and there should always be a corresponding delete to a new, but this is how it might work. So int star p equals new int on the heap, please. And then suddenly now, maybe this was main. So in main stack frame, for example, maybe I can make it up here. So there's just one method call. So main holds p. P is box because it holds a pointer. We gave it a name, so it's got to live in the stack. But it holds the address on, this is the stack, by the way, on the heap of this brand new int. Okay? So every time we say new int, it makes a shiny brand new int on the heap and gives us back a pointer to it. Maybe its address 100, my favorite. So p would hold the number 100 because this is address 100. Okay? And so p is the only way you can interact with this variable. Okay? And then you'll say star p equals 42, for example, to set it. Set the value there, and then you can use it because initially it's always undefined as normal. And then once you're done with it, you can say delete p. And that gets rid of it. Okay, now you can't use p anymore. Okay, that's the corresponding life of a thing. It doesn't care that your function returned. It's going to live there forever as long as you ask it to, until you say delete. Okay? So the heap is a different place in memory. The second you lose access, because you have to reference everything on the heap with a pointer. Everything on the heap is, you can only access it with pointers. If you lose a pointer, if you lose your only pointer, or your last pointer, to something on the heap, there's no way for you to delete it now. So for example, maybe this was not main, but it was like foo or something, and foo returned. Then suddenly you lost p, which means you lost this one reference to the heap for this thing. And that's a memory leak. Okay? We don't like that. So let's say if this were foo, and foo returned, you lost access to p. That is no fun. So that is unfortunate. And yeah, so let me, I guess I showed you this example already, storing a single int on the heap. That's essentially all this code here. And in the interest of time, I'm not going to type it up. My last example, example 2, is let's use an array of things. So to make an array on the heap, we'll say new int, and then give the size. Okay? And then we can make an array as big as we want on the heap. And we can delete it with delete bracket bracket. Okay, so delete bracket bracket is for arrays. So let's get a number from the user, make an array of all that many numbers, and then calculate the median of that array. Okie dokie. So, heap.cdp. So let's get a bunch of numbers from the user. We'll be like, how many? Ask the user to give us that number. And then we're going to get that many numbers from the user. Okay, and then we'll put it into a heap array. So the second we have the number of things we need, we'll just say int star arr equals new int of size n. Okay, makes an array of size n on the heap. And once we're done with it, we'll have to delete it. Delete bracket bracket arr. And so arrays, remember, they're also pointers to their first object, to their first value. Okie dokie, that's that. And now we can just fill in the array. It could be like, all right, array at I equals next num, and then we can find the median. Let's quickly calculate the median of things. The easiest way to do it would be to sort the array. So let's sort. There is a sorting function inside of algorithm, and here's what we can do. We can say algorithm. We can say sort arr plus the size. That's how we sort the entire array, and now the middle index is the median. The issue arises if this was an odd-sized array, but that's beside the point. So if n, the size of the array, mod 2 is, now if it's even, then we have to average the two middle indices for the median, and then otherwise the middle index is the median. Okie dokie. So let's pretend our size was like 6. If our size was 6, we needed to get the middle index. It has 0, 1, 2, 3, 4, and 5. 6 divided by 2, integer division is 3. That's one of them. I need 3 and 2. Okay? So if n mod 2 is 0, we need first index equals n divided by 2 minus 1, and then second index is n divided by 2. Okay, otherwise it's even, and so we have like size 5, 0, 1, 2, sorry, it's odd. 0, 1, 2, 3, and 4. 5 divided by 2, integer division is 2, and that is the middle. That is the middle index that we want. Okay? Cool. So now we can be like, okay, see out the median of this, in this case, is array at first index plus array at second index divided by 2, but we need parentheses, of course. There's that one, and we'll see out array at mid. And that should do it. Just a quick little example of using heap arrays for something. So like, oops, what have I done wrong? Oh, I need to comment all this stuff out. Excuse me. I'll just delete it. How many numbers? Let's do, I don't know, 6. 1, 2, 3, 4, 5, and 6. So the median should be, oh sorry, 3.5. Oops. That'll do that. How dare I get it wrong? There we go. And then, alternatively, there's 5 numbers. 1, 2, 3, 4, 5. The median is 3. Cool. And then we'll delete our array that we made on the heap because we're done with it. And this can all exist across function calls. That's all beautiful. You can swap with pointers. It's just a grand old time. And that is the first part of this review now. So I've gone over in detail a lot of these things that I don't want you to forget if you have to take CSCI 41, and also because you're definitely going to take the final. Now you know about them a little bit more. They're ingrained in your mind a little bit stronger. So that's the older stuff, and we'll come back in the next lecture for the newer stuff. So I'll see you then.